All right. Good day to you. We're going to go ahead and get started on my favorite chapter or module of the course, which is particle systems. And it's actually a really simple thing to do because you pretty much already learned everything that you need to know to implement it. You know how to create an array of movers, and that's pretty much all a particle system is, except for some specific behaviors, such as a particle system is just a mover that you stop drawing when a lifetime or some kind of lifetime or some kind of time limit on when that mover or is no longer rendered on the screen. And that mover can be a lot of different things, and I use that term mover lightly. It's just a sprite that moves around, essentially, and it's moves around automatically. If you're going to have something else like a character, we like to refer to the sprite term. So I believe it comes from your book, but for a particle system, essentially you're going to draw these movers on the screen and set them in motion, and you have to stop drawing them at some time, which means that it's a hard mechanism to deal with and get working correctly if you don't know how to do it. And I'm going to give you a good demonstration on that capability, and we'll talk about some of that through the PowerPoint. So let's go through your objectives, and then we'll hit the PowerPoint, and then we'll go have some fun. So your objectives is to describe pooled memory, recite why pooled memory is needed for managed code, such as Java, C#, and JavaScript, and all the other ones out there. Apply multiple forces to particles and create render particles. So when I say term particles, that's just a mover. That's all. It's just how we're dealing with those movers as an array. And here's kind of what pooled memory, the whole idea of just pooled memory. It refers to a way that a game is created, and often, just like with any application, you start up the game and it grabs all the memory it needs. It creates the arrays. And so pooled memory is just your array. That's all it is. It's a fancy term, meaning and how you react with it, because pooled memory means that you create all the memory at the beginning of your execution time or interpretation time, and that memory is left on the stack or the heap for you to access throughout the entire time your program is activated. And it only is released when your program is done. And other languages such as C and C++, you have to literally create that memory explicitly and then explicitly free that memory. And that memory is mostly created with a new, just like in JavaScript, they use the new term. And that's what creates memory off the heap, is using that new term. And that, for managed code, is a killer, because what we have is what's called the garbage collector. And the garbage collector is always waiting to see if you're done using memory, or when memory goes out of scope of where you're actually using it, and it frees it up. So if you're continually using that new operator, there's a time where your application needs to free that memory up. And if you're using that new operator for particles all the time, you are spending more time creating memory and removing memory instead of just reusing memory. And that's the idea of why pooled memory is needed, because even in normal application or other applications where you don't have a garbage collector that keeps track of all the memory you create with the new statement, you still have pooled memory where you create all the memory you need and free it up at the end just because it's faster. But with managed memory, you just create it and roll with it, and the garbage collector manages it, which means that the more memory you create, the harder the garbage collector is working. So you need to reuse the memory instead of creating new memory each time you need another particle to show on the screen. So memory pooling, I'm going to describe. Or I'm going to give you an example of it today, and then we're going to create and render those particles from pooled memory, while also applying forces to the particles. And you'll get a chance to play with it and add your own forces to the particles, or add more forces. But anyways, a particle. When I say particles, I'm talking about a mover. It's just with pooled memory and some kind of renewal for the memory, so that you can reuse the memory instead of just creating new memory all the time. So that means you got to build it. You got to build. You got to create the array, and then have something that keeps track of what memory is being used, such as like a variable inside of the mover that refers to its lifetime. So let's go ahead and hit the PowerPoints, go through those, and then we'll get in and start playing around and having some fun with the code. So let's go ahead and start with this bit. So there's some actually code. We're going to hit some of the code right now, and then we're going to get started on some of the assignment. Okay, so this is pretty much a review. I'm going to go ahead and skip this. You guys can, of course, read it, pause it on the screen. But this is kind of everything we followed or we've created, and kind of the main big ideas. Okay, so here is a question: what is a garbage collector in reference to memory or RAM? We just talked about it. All right, so this is an example of particle. So you can kind of think about the particle as just a mover. That's all it is. It's being called particle. That's all. And it's going to have some attributes to it. You can add images so that your particle has an image, but what I've done is I've just decided that I was going to just draw a circle. You could actually apply some cool techniques to that circle that you're drawing and give it kind of like a globe effect, where you can have like a magician throwing balls of fire, that kind of stuff. It's really cool stuff. So this is kind of how you would implement also a machine gun, or some kind of projectile that was always going to be rendered but had to be renewed on the screen based on a user action. So the attributes of this particle, the main attributes is the lifespan. That's how it's most different from the mover class. And so what we have is the typical location, acceleration, velocity, angle, mass, width, and height of the particle, which are also our starting arguments. We're going to send the initial starting location of the particle. We're going to have the width and height of the particle, which is going to be used to draw a circle. The angle of the particle. Then not only do you have an angle of the particle referring to the angle of how it's drawn on the screen, which doesn't matter because we're dealing with a circle here, but you could draw this as a square and refer to how the square is drawn on the screen. And then here's the main one, direction. That is a vector on where the particle is going. So we're going to actually apply direction to velocity. We should be applying it to velocity right off the bat. Here we go. No, acceleration, not velocity. Well, it looks like I do give it to acceleration, but guess what? Acceleration is added to velocity, so it doesn't really matter. So we start out the particle going in the direction that we pass in, and then that's going to be significant when we start generating the particles, because now we have a lifespan. And the lifespan is used to describe whether we draw it on the screen or not, and or whether that particle is something we need to take into account, such as maybe a machine gun and it's a bullet. When we refer to the lifespan, that's when we start treating the particle as if it was dead. However, it's still in the pooled memory. So what we have is, once we create or instantiate the particle, we have to use these guys right here, these x, y, particle width, particle angle, direction, lifespan, and mass, as default arguments, or when we instantiate or create the particle. And then the lifespan, if you look at the draw function now, if you see here the draw is going to take care of all the issues of drawing, but we only want to draw, or we're only going to call the draw method if the lifespan, if it's not dead. So we're going to be detecting whether or not this particle is dead. So we start the particle with a lifespan, say, of just number 10 or something. And every frame, maybe we subtract 1 from that 10. So that means that it will have a lifespan of 10 frames. So that's something you play with as you kind of get, what kind of number should I give this particle for a lifespan? And you play with it, and that's one of those arguments you just kind of see what happens. So we're only going to draw or call the draw method if we detect the particle is dead. So that's what this lifespan variable does. And if you see here in our update function, we're subtracting lifespan by 2.0. So that could be another argument that you send in, like the lifespan decrement, how it decrements. But here is the key, this renew function. So when you want to create the particles, you run this argument. Then the particle's lifespan goes and it dies. And so in the update function, it eventually dies because you're going to say send 10 in as your lifespan. The particle will die, and essentially then you want to renew that particle so that you can render it on the screen again. Let's say the character hits the trigger button to fire off some bullets. So then you renew that particle in the memory pool, and you send it a new direction, its starting location, of course its angle, and then a new lifespan for the particle. So I mean, this is a system for a lot of things that you find in the game as a particle system. But you can just kind of think of them as fancy movers. Pretty much, that's what they are. So that's kind of the attributes of a particle. And then we get into the emitter. Now the emitter is important because it's what's controlling all the renewing and the updating of the particle itself. So this would be your machine gun. And what it does is it holds, it's an object that holds an array of particles. That's all it is. And an emitter can have its own location, acceleration, velocity, mass, angle, and everything. I mean, think about if you're building a firework. A firework could be an emitter, and if you wanted that firework to spin while it's emitting, like a universe or whatever. So an emitter is what handles the memory pooling of your particles. It's nice to put it all in one thing, so you can have multiple emitters. Or you can have an emitter of emitters. Yes, it gets kind of crazy. So this emitter object, you will send it the variables that you want your particles attributes to be, and then you create an array of particles. Now with that, here's what you have to deal with is we get it started by creating or adding one particle. This is just some runtime down here. But what ends up happening is we need to pool the memory. So that's got to be what actually happens first. So let's look at this here. Our constructor goes through and assigns the normal variables that we need. And then our array of emitters created right here. Now you notice this is a new array. And this is a new. These are okay because emitters are going to be pooled. This is going to, an emitter is going to last for. We're going to create an emitter that's going to have create a pool of particles on instantiation. So we'll say, okay, give me an emitter or a machine gun, and let's go ahead and pool 200 particles in it that I can recycle through and show on the screen, kill and show on the screen and whatnot. So. You've got to actually create that those actual particular particles inside of that array, and I believe we've got with the code here, we have our memory pooling. Now notice it's called right here, pool memory. This is actually called first, and then it runs through it and it pulls the memory. So here's what happens first. Particles array is created. Then down here we call pool memory. And then what it does is it fills that particle array with new particles. And this is where we pass in the variables we want the particles to have. That we send the emitter, such as the direction, angle, and the starting location, and the width and height of the particles. So it is all with these ones that I have in red on how to pool memory. So once we create the pooled memory, and this is runtime, we pool the memory, then we go ahead and add 3 particles. We just start off by adding 3 particles. It looks like 3. It says add 1, but I think it's like 3 particles. So this add particle function, and what this add particle function does is it goes through the array and it says, hey, is there a particle in here that's dead? If you find a dead particle, oh, I can use that particle. I need a new particle, but I need to use my pool. So what this array does is it walks through the particle array that's created here, particles, that's instantiated and pooled down here. Then you say, okay, I want to show or render our particles on the screen. So then you go through the whole particle array for however many particles are in that array. You will look at every particle and say, hey, is it dead? If it's dead, then that's one you can renew and redraw on the screen. So you set a direction with a random variable. I've got some random things. You can change that with the direction variable up here. So this would be something that would need to be fixed right here. Change this to the direction variable. So set it to the direction. Oh, wait, no. We're just resetting the direction variable. Excuse me. So we get the direction vector for the particle set up. Then we renew the particle. This is what makes it work. We send it the new direction, new starting location, the angle, which is we're not even using. But here's the key, a new lifespan, which then the particle, once it's renewed, you go through the whole particle again. We're in the update function. You go through the whole particle array again. You update the particles, and you don't want to put an if statement here. Just depending on the pool, there's other better ways of dealing with this. But you update the particles, and then you go into the draw, and only if the particle, if you see here, only if the particle is alive do you actually, it says if not dead, do you actually draw the particle. So there'll be a way that there's other ways that you can get so once you write code like this, you're going to end up trying to find ways to get rid of these if statements. That's your bane. The more if statements and the less memory you have to go through, the better. But since we're going through so much memory in our pool, there's definitely ways to get this more efficient, I guess is what I'm trying to say. But this is an introductory, and I want to try to stay as simple as possible because it's complex enough. So first thing we do is particle instantiation. We declare the array right here. So this is our emitter. It's going to have the ability to have multiple particles. So each particle you think is basically you refer to as a sprite or a mover, and we're going to create and define an array of particles. So first we define the array of particles inside the emitter. Then we pool the memory that we're going to use for the particles, for how many particles there are. That means we've got to actually instantiate it. This is where we're actually grabbing from the memory from the heap, and we're pooling the memory because an emitter is going to exist for the lifetime that an emitter needs to exist on the screen. So you could actually set it up so you pool your emitters too, that then pool their particles. So This is where we actually instantiate the new particles, and now after this runtime line of code is run, now the particles are ready to work. So once the particle's lifespan is reduced through the update function, we need to have this renew function that will then add more lifespan to the particle on demand through the add particle function. So the this is dead function is just basically, it looks at the lifespan of the particle, returns true or false. This could actually be turned into a tertiary if or a ternary if statement, which would greatly increase the efficiency. So this is highly inefficient. So then the add particle, what it does is it goes through the array of all the particles that are available, and it finds the ones that are dead. If it finds a dead particle in the array of all your pooled particles, then it sets the direction that particle is going to go into. You should probably replace this with whatever direction was passed through when you created the particles, or actually, no, the add particle sets the direction right there. This is going to be, you would probably just get rid of this whole line, and the direction that you send in would be what this whole line should actually be removed. But this is the main line right here. You renew the particle with a direction, and you can decide to change it here or just use the one that was passed into the function. So the direction is set when you renew the particle, its starting location, whatever angle, which doesn't matter because we're dealing circles, and then the lifespan, the new lifespan of the particle, which I think are hard-coded to some kind of value like 100 or 10 or whatever. So the update function reduces the lifespan by 2 for every frame, and then the update function goes through the whole memory pool to update the particles. There's a better way of doing this. Instead of going through all the particles, but then again, you never know which ones are going to be in use. So a way to do this with more efficiency is probably have a binary tree type memory pool that would increase efficiency, because this is highly inefficient that we're going through the whole array of particles just to update them. Now right here is where we go through the whole array of particles, and only if the particle is not dead, there's a not in front of there, only if the particle is not dead do we actually draw the particle. And then since I want to make this this draw function kind of adding particles as we progress, I just went ahead and add this line. This is actually what makes it all work, this last line. This add particle is what actually makes everything work. So every time I'm drawing, or the draw function is called in the emitter, I draw all the particles that are alive, then I add new particles. So every time the draw function is running, I add particles, or the top proper term would, I renew particles. And it looks like I'm doing 3 particles for every frame. So if you look at the add particle function, you'll see that it takes, what is it? It's, so it takes a count. How many particles do you want to add? And what lifespan of particles do you want? So it looks like I am adding 3, and I'm passing the lifespan that's defaulted. When we notice this dot lifespan, I'm passing the lifespan that was passed to the emitter on instantiation, or when the emitter was created. So it adds 3 particles every frame, and it does it at the center of the x and y coordinates. Okay, so anything that you instantiate off the heap that goes on memory that your application or set of instructions has access to, you should reduce as much as possible anytime you use the new operator. Pool as much of that memory that uses that new operator as you can. And mostly always that when you use that new operator, you're doing it for significant things in your code instead of just a localized, like a simple variable that you use in a function, just like integer I for a loop or something like that. So if you're using memory, you should be pooling it as much as possible. A simple way to think about memory pooling is your sprite that you created for your assignment and have walking around the screen. That's pooled memory that works throughout the whole throughout the whole scope of your application, and mostly it's created at file scope and also referred to as a global variable. But here we're doing it inside of an object. Which is safer and better. Okay, so some challenges for you to kind of think of with this code that we've kind of gone through. We're going to actually use some different set of code, some templates, but I believe I have some code that you can play around with that is associated to this PowerPoint. So try to create an emitter of emitters, change the direction of the emitter, change the amount of emitters, change the size of emitter. So I'm talking about an emitter which would be an array of particles that are inside the emitter. So make your emission narrow or wider. So the emission that I'm talking about is the example that you find for your assignment that you're going to create, which is this emitter right here. This is an emitter, and its location is here in X and Y, and the emitter is emitting its pool of particles that then travel across the screen based on your starting velocity, and then it's going to slowly stop drawing them as those emitters die for its lifespan. Okay, I'm going to go ahead and pause this, and then we're going to go and have some fun because it's time to create and render particles and apply multiple forces to particles. I'll be right back. Okay, we're back. So I've got ready to I got our template downloaded. It's this one for assignment 1. Download template for assignment number 1. And when you unzip it and open it up in NetBeans, it's titled Chapter 4 Particles Assignment 1. So let's go ahead and look at the code. Let's start with our normal index.html. We can see here we got our common math vector, and then particle.js. I wanted to make this as simple as possible, so we got a pared down version of our code that we've been working with. The only thing that we've got is particles and the vector class. So let's look at the math vector class, which is first, and let's get rid of that poopy code. So that poopy code is those add functions. Okay, so this is good add function. This is poopy add function. Notice how it uses the new. This just adds using the existing memory of the left operand with the right operand when you use. So you're running this add function on a vector that adds the other vector to it. So you're using the vector that you're adding to, this.x and this.y, and adding it to the other x and the other y. That's what that plus equal does. Okay, so poopy add function gone. And I think we did this last one. Poopy subtract function gone. Okay, now the next one, let's see. Is there a div? Yep, poopy div. Get rid of it. Okay. That's a divide by. And that's mostly going to be for like mass or something like that. Okay, so I think we're good. Let's do a save all. We got rid of those. Hopefully we don't have to do too many edits to fix anything that caused a problem from the original code. Okay, so got rid of those add function, the add, subtract, and divide function that uses the new. Okay, so that's the divide again. Save all. Now we're going to go and we're going to look at the next bit in index.html, and that's our particle class. So we've actually already covered, I already talked about the particle class, but let's see what we got here. We've got a color to use. It looks like that's done at file scope, and it looks like I put in an ellipse in here so that it's probably Chrome versus Firefox has issues with one versus the other. So I created an ellipse object that uses the arc function that's available to pretty much every browser out there. So this is just to draw a circle. That's all it is. Now we get to our particle class, and that's just everything that we've already covered. We got to renew our update. Everything's pretty much the same. We have our add. Now this is kind of what I'm talking about. This.x plus other.x. This.y plus other.y. And that's how this add function works, or the sub. That's what this.x is. So it's referring, since we're running the add function on velocity, we already have velocity's x. So we're just going to add the acceleration's x to the velocity's x without having to create the new, or have to use the new. So we're essentially just reusing this velocity variable to add the velocity x and the acceleration y, or acceleration x together, and then the new value is stored in velocity x, which is exactly what we want to do. So the same thing with location. Location x plus other x. And that's kind of how that is. So when I say this.x, we're referring to that left-hand operand, and this is the right-hand operand. Left-hand operand, right-hand operand. Okay, so now we have everything. We have our draw. We have our lifespan is dead. Then we get into our next bit in our index. So we've covered all that. We got our canvas. Okay, what's going on here? Okay, let's get rid of some of this stuff. I already can tell right now I'm not liking this. Let's get rid of all this. It's driving me insane already. We probably could get rid of this, or just keep, I don't know. We probably don't need any of the, let's just keep all that other. Let's get rid of this. Let's fix this guy. Boy, I think we do this every time, don't we? Okay. Well, you know, improvements are always good. Okay, so let's go to 0, 0 and just clear the whole canvas. Okay, so that's good. Update all variables. Update your particle objects. Draw. Okay, calc FPS can get gone. Then we have our setup function. Call setup before game loop is called. This is where we're going to actually call or pool our memory right here. We're going to pool our memory in the setup because this is going to happen before our game loop begins. Get rid of this. We don't need this diagnostics thing. So we call the setup function to pool our memory to create our emitter before our game loop starts updating and drawing our emitters. They got to exist first. So that's what that setup function is going to do. Is it's going to create an emitter that then pools the particles. Okay, so we can get rid of this calc FPS. We'll keep the clear canvas. We'll get rid of this right here. So we just have clear canvas, update, draw, and whatnot. Okay, so basically this isn't doing anything. So let's go ahead and look at our steps. First off, let's just make sure that we don't have any, we may have some obvious errors, but probably shouldn't do anything. Yeah, doesn't do anything. Okay. All right, let's go look at our steps. Step 1, modify canvas.js to declare an array of particles. Place the following line towards the, this is, I gave you, the emitter is more for the example that I posted in your template. So you're going to be doing a little bit simpler example of your particle emission. So our emitter is going to be canvas.js. So we're going to be building our own emitter within the game, the game itself. So I would highly recommend putting this stuff inside of an object called emitter, though. But I wanted to keep things as simple as possible for you to just understand what particles are and how to renew them and deal with it. So what we're going to do is we're going to create our array of particles. Now that's going to be done at file scope because it's going to be, it's going to be a variable that we're going to be using throughout the whole course of the game, pooling that memory that's going to be available to every function and object at the top level of the game. So this is also why it's better to pool or to have this in an emitter object because it's an array that's it's a global array, and that's just kind of not. It's a little on the scabby side, but again, we're starting at the beginning. We've got to learn this stuff before we move on too much. Okay, so let's create our array of particles, and what we're going to do is we're going to put that at file scope so that everything has access to it. Now, when I say file scope, that means that clear canvas, update, draw, setup, all these variables in my canvas.js or all these functions will have access to it. So we're going to put it up here at file scope instead of in here in the function so that everything has access to our array of particles. So our array of particles is set. Now we've got to instantiate each particle in the array. So first we instantiate the array itself, and then you have to go in and instantiate every particle inside of the array. And that's why most of you guys have problems building arrays, is you didn't understand that. When you're actually doing an array of objects, you got to instantiate the objects inside the array. If it's just a simple data type such as an integer, double, or whatever, you don't have to instantiate the variables inside of the array. It's automatic off the stack. So here we're creating an array, a pointer to an array of particles on the heap. So that means that we've got to instantiate each particle, and that's going to be done before our game gets started. So we're going to pool with the setup function. Okay, so let's go look at step 2. Instantiate your array of particles by placing the following lines of code in your setup function. Okay, so let's go ahead and throw that in there. Okay, so setup. Okay, so let's make that look a little bit better. Okay, so what this is going to do is it's going to instantiate. It's going to be called before the game loop starts. And it's going to go ahead and create new particles. And what it's going to send to the particle is just looks like an origin, an X and Y value for where the particle should start. So if we look at the particle class, it looks like it's designed to just take on a starting point, and we're going to hard code everything else. Everything else is hard coded, such as the direction that it's going to travel in and everything else. This is where you would definitely want to do something like that emitter code that I showed you in PowerPoint that's also available to you with the other template that goes along with the PowerPoint. We instantiate our particles with just a starting point for the particle, and this other stuff is hard-coded. Okay, so let's go back to mycanvas.js, and it looks like we have our setup. We've instantiated our particles. We send it the middle of the screen as coordinates for the X and Y. So let's go to step 3. Step 3, update. In Canvas update, we need to renew 5 particles every frame. So what we're going to do is we're going to loop for 5 times, and we're going to go through. We want to create 5 particles. So we have to go through the array 5 times to find a dead particle that's not being used. So the more you so essentially these two things are highly inefficient and can be solved in different ways. However, you are just learning now, and now I've kind of got it through to you that if statements are a huge thing, and that you should build and design your mechanisms in a way that you use math instead to solve your problems. There are ways to get beyond these issues, such as coming up with a binary tree type system, which is way beyond where we need to discuss things. So we're going to keep it as simple. So I'm going to, for every particle that I want to create, I go through the whole array of particles to find a dead particle that I then renew. Now, you notice this break here? This is very important because what this does is as soon as I find a new particle that I renew, I break out of this loop. So it's not totally inefficient. So it doesn't go through the whole array. It just goes through the array until it finds a dead one, and then it comes outside of the for loop. And that's what that break does, is it breaks it out of the for loop, and it comes back and it goes through and tries to create another particle. So basically what this does is it'll go through the array of particles until it finds one that's dead, renew it, and then stop going through. It'll then come back to this loop, which will then say, hey, I want another 4 particles. And then it'll go through the loop again, find a dead one, break out of the loop, so that you're not going through all the particles to find a particle that you need. If you get, say, the first one that you get to is the one you need, therefore you no longer need to go through the particles. So this double mechanism is very essential for having everything work properly. Okay, so we're gonna actually put this in the game loop. So this is what actually does the mechanism of creating particles. Every frame we create 5. So that means then that we are forced to go through all the particles and update them and reduce their lifespan. So let's go ahead and go through here. The update function in the particle itself is what reduces the lifespan. So I'm going to copy all the code for step 3 here. And then we'll go on to step 4. So the particle update, go ahead and look at it on your own. It should reduce the lifespan of the particle. Okay, so let's go ahead and go back to our project and put this in here. Okay, so that's doing all our main tasks for both updating all the particles and the main task of creating 5 particles every frame, or renewing 5 particles every frame. I imagine that this is probably overkill and that you could tweak with these numbers, but that's why you have an emitter system, is so that you can send it some variables to define its behavior on how it actually renews and all that stuff, and get all those little numbers down, and so that it looks good and behaves properly, which then kind of goes into, oh, shouldn't I consider frames per second when I'm doing all that? Yes, you should. If you're building a real game, you would have ratios that you depend on all the time, such as screen size, character width, and height. That is a ratio of the screen size, so that when you change your screen, your character enlarges or decreases based on the screen size. That's a ratio. Also, another ratio that you would have is frames per second, because you wouldn't want to hard code this so that it's stuck on the speed based on the processor speed. But then again, we've kind of already solved that problem when we have the callback loop only happening every 14 milliseconds, which is 60 frames a second. So, there's a lot that goes into that. But in any case, we create 5. This creates our 5 new particles to show on the screen by renewal. This will go ahead and update all the particles and reduce its lifespan. So we do that for every update. Okay, let's go ahead and go to step 4. We go into the draw function, and we only draw if the particle is not dead. So you notice that little exclamation mark in front of there. So let's go ahead and step 4. Let's go to the draw function of the canvas. And let's update the particles only if they're not dead. So we only draw them if they're not dead. Okay, so we instantiate the particles. We instantiate the array, then we instantiate the particles. The setup then calls, the setup is done running. Then we go into the game loop, and these 4 steps happen over and over and over. Clear canvas, update, draw. Clear canvas, update, draw. Clear canvas does its job, update. Generate 5 particles. Reduce the lifespan of all particles. Draw. If the particle is dead or not dead, only draw that particle. Okay, let's see if it actually works on the first shot. Yeah, I'll tell you what, this is my favorite chapter. I just love particles and playing around with them. Okay. Looks like we got an error, so let's go ahead and look at our developer tools here. Okay, so let's see here. I is not defined. Uh-oh. Did I miss something? Let's go back to step 4. Where is that? Is it step 4? Okay. Oh, 4, all the particles, if it's not dead. Okay, that's a little, okay, I missed that one. All right, let's do this then. Let's copy this. Step 4, I was right, it is step 4. Okay, so let's go ahead and go back to our thing and do this properly. Because you got to loop through all the particles to decide whether or not you draw them or not. Okay, so this is all proper indenting I'm doing. All right, now we're good. There they are. God, I mean, you can just have so much fun with this. How about adding bounce around the edges or something like that? Adding just regular wind force to have them blowing to the right or something. In fact, let's do that. I think that's one of your challenges. You can add another one on your own after we do that. Let's go ahead and look at the next steps. Okay, completed application. Good, we solved that. Okay, so step 1, review chapter 2 forces, section 2.2, 2.3, study and locate, apply force function of particle.js. Okay, assignment 2, using template from assignment 1 and the apply force function, located in particle.js, add forces to your particle such as wind and gravity. We can add the force to all the particles either in the particle update function or the canvas update function. I think we should do it in the canvas update function because that's kind of representing an emitter. We want to apply a force to all the particles. So let's go ahead and do that. First, let's look at the particle apply force function. Okay, it looks like it's dividing by the mass and doing an add on the acceleration of a force F. So first we divide by the mass. So we might have a problem with that mass variable depending on what's being set. It looks like nothing's being set for this dot mass. So that means that we probably need to set the value of this dot mass because I don't think it's in here anywhere. So we got to actually create that. So we'll do that in the particle because that's what this means. So we'll do this. We'll do this dot mass is equal. Now we could do a random here, and all these new variables are okay because it's all pooling particles. We can do a random, but then that would mean the size of the particles would change. I don't know. Let's just throw in a value like 1. No, let's make it interesting too. We might play with that later. Just throwing because we're gonna see what happens basically. So we're gonna run the apply force function every particle is going to have a mass of 2.0. The force is reduced by the mass of the particle, and then we add the force to the acceleration, which then adds it to the velocity, which then adds it to the location. So you see here, location. Ah, look at this one. This is poopy code right here. The location is already created up here with the new. So the renew should not work in this manner. So if you wanted to optimize this anymore, you would get rid of this new. And you would just reset the location X and Y. And for example, you would do this for the renew. This would be this dot location. Why should you renew it? Okay. And then you would set the acceleration. You would just do dot x is equal to blah dot y. So this is horrible code practice right here. Why use the new? You could just reuse what you've already created up here. You've already used the new here. There's no reason for you to create another new, which then creates another variable, which then the garbage collector has to clean up the one you created up here at particle or object scope. So this is just horrible code. Okay, I just want you to know, I'm not going to go any further. This is an example of how to create it or how to change it. Let me give you another example of how to make it better. This dot acceleration dot x equals 0. This dot acceleration dot y equals 0.05. Okay, you kind of get the idea now? That's proper code for the renew function. Should not be using the new. You don't need it. So let's just get rid of them all. Heck with it. Okay. Okay, syntax. Okay, velocity is matching up. So you see what I'm doing? I'm clicking on one of them, and it highlights up here, just so I know I don't have a misspelling. Okay. Okay, looks like that's all looking good to me. Okay. Oh, we're going to apply force. We're going to add gravity to this. Okay, so let's go into my canvas, and what we're going to do is we're going to add a wind force. We're going to add a wind force to every particle. Now, where are we going to do that? Well, if we're going to apply a wind force to every particle, we could do it in two places. We could do it here for the update. We can go into the particle. We can send the force through the update function. We can apply the force to the particle before the update, which I think would probably be, since the particle has an apply force, doesn't it? Yeah, the particle has an apply force. So we could just, before the update, we could say particle of I dot apply force and send it a force, which is going to be just a vector, p vector, wind equals new p vector. Oh, poopy code again. Don't do that in a loop. In fact, I would just create the wind vector up here. And then use it. Just reuse that force over and over again, instead of actually, creating a new inside of a loop. That's just your nemesis. The new statement's your nemesis. Every time you use it, get rid of it as much as you can and only use it for pooling. Okay, so let's have a 0.5 wind here. Oh, that's not wind, that's gravity. That's going to blow to the right. Okay, so we create a wind force, and now all we're going to do is we're going to pass that wind force into every particle's apply force function. Simple and easy. I love it, and fairly economical. So now we get to play and see if we got some wind blowing on our... Whoa! That's some freaking wind, man. Woo-hoo-hoo! Now you see why I love particles. So some things to try. How about let's widen this fan out. Let's widen that fan out. How would we do that? Well, we could go in the direction that we set for every particle. We have a location, but we set a direction. And that direction, it looks like we're hard coding inside of the particle code itself, I believe. Because when we renew it, I believe we're just setting in an X and Y. So let's look at the particle code. And this is probably something that you can do somewhere else, but it looks like right here. This is it. We're setting the velocity right here. Let's say we wanted to fan it out more, and we wanted it to fan out more up and down. So what we would then do is we would increase the range of the random values to a -6 and 6. Okay. Something else is going on. Because that doesn't look like it really fanned out too much to me. Are we actually applying a new velocity when we get renew? Oh yeah, here it is. This is what's doing it. So this is actually not even doing the work. It's just starting it out. It's only when we renew. So you notice this is hard coded. This should not be hard coded. So it looks like the velocity Y. Let's say that we want to go an even fan to the right. So let's do a -6 with a +6 value. So it goes up and down between -6 or 6 pixels. Wow. Okay. That's a very interesting emitter there. Okay, so for your renew function, you know what you might want to do is you might want to send a direction vector in here instead of hard coding it with some random values every time you renew the particle. And remember, this just happens once right here. You've got it every time you instantiate a particle, you have to instantiate your objects inside. So this only happens once, and you pull that memory inside of your particle array, and then you just reuse that memory in this manner right here, like I showed you, and also other places where I've kind of taught you how to reduce and increase your efficiency, which is kind of the law, the nature, and that'll never change. If you are ever able to find a better way of doing a job mechanically or process-wise, something that's faster for something that's used all the time, you can write your own check, literally. Some of the newer, every time a new algorithm comes out for, such as collision detection for a game, I remember some of the games throughout the years that are coming out for some of the first-person shooters. The companies that were able to solve the problems and have the best feedback and speed, etc., and the most efficient code are the ones that literally are the only ones that can make it. So efficiency in your code is your job, regardless of what industry you're working in. No matter what, a computer's intelligence and usefulness is always based on its speed. And if you remember, just remember this: a good programmer is a lazy programmer. And why? Because they solve problems with less lines of code. The more lines you add, the worse it gets. All right, guys. I would like you guys to add some more of your own forces. change some colors, get some different directions. Maybe create like a firework one where it all goes around and emits in a circle like a firework. So, you know, what you could do is you could add colors to your emitters, have your emitter go from, you know, -6 to 6 for both axes so that it's coming out like, you know, a firework. In fact, let's just play with that. Let's do this just for fun. Maybe create a fire. Oh, okay, so maybe that didn't work. Okay, you guys are gonna play with this and have some fun. Add something to it and make it your own. All right, thank you. Have a good one.